We have fantastic guests and speakers on stage. It's time for our first keynote with Professor Aude Billard, titled Cobots Deployment. Imagine you are walking to work and suddenly a small robot passes you on the sidewalk. How do we optimize the usage of autonomous mobility devices in populated areas? And what are the risks and how do we communicate them? To further discuss these topics is Professor Aude Billard, full-time professor and head of the LASER laboratory at the School of Engineering at the Swiss Institute of Technology in Lausanne. And she's also the director of the Swiss National Theme Innovation Booster Network in Robotics. A warm welcome, Professor Aude Billard.
Good morning, everybody. It's a pleasure to be here.
Hello. Professor Billard, what is your last mile delivery favorite? Would it be a drone or a legged robot?
You mean what was the last delivery that I ordered?
The last mile. What is your favorite cobot?
My favorite cobot. It's processes. Any type of processes, I consider those as cobots because they do work with us, with our body, basically.
Yes. So I will leave the keynote to you, and afterwards we have time for questions, and I've already explained to the audience how they ask questions. So I'll leave the 20-minute keynote for you, Professor Billard.
Sure, with pleasure. Thank you. So yeah, thank you very much for this invitation. Also, I think I just wanted to say it's wonderful that you organize such a digital conference and you do not expect people to travel. It's been refreshing. There is always this push for one to travel on site, and it seems that you're doing the exact opposite. That you're really striving to have something fully hybrid, and I welcome that very much. So thank you. So I wanted to talk to you today about a particular type of cobots, which are those robots that we may already see tomorrow within our daily life, and to discuss a little bit about what type of guidelines we need to have to minimize the risk that they may generate for us humans and really have only the full benefits that this platform can bring to us. So the robot that I have in mind, as I said just a second ago, are robots that enable us to do things that we couldn't do before. Prostheses in all type of types. So we have on top here hand prostheses or also leg prostheses, which enable people to recover some of the mobility of the upper limb or the lower limbs. I'm particularly impressed by the work done by one of my colleagues on the bottom right that enables someone to climb stairs again, an extremely difficult task. The other type of mobility that we already see being deployed slowly are this type of standing mobility device. They enable people who have lost the leg mobility to be able to navigate in the streets. It's like a wheelchair, but it's a standing wheelchair, so standing mobility device. It has the advantage that the person is at the same height as other people, other pedestrians. And so it can be guided with only a very simple remote control on the upper body. We've been fortunate enough to collaborate with the University of Tsukuba that developed this system, and we've worked primarily on making it safe and fully autonomous. And so I'd like to discuss with you a little bit what this means to deploy these robots in the streets. So. As you know, there is really an interest worldwide to deploy robots in the streets on pedestrian lanes. This is not just about having mobility device for people disabled. It's also about carrying goods. It's also about helping people being more efficient by transporting different important things such as blood samples from one hospital to the other. There are regulations for the deployment of those robots. There are many different regulations on which one can base the deployment. And all of those, what they regulate primarily are speed limitation, how fast can the robots move when it's within the vicinity of pedestrians, some core norms, and also, quite importantly, guidelines for the design in such a way that the robot is not dangerous. Yet, I think we need to be aware that there is a need for a little bit more guidelines, because there are some risks that are not taken into account by those standards. And so in this view, we started doing crash tests with the wheel-based platform that I showed before. So this is the same standing device that you have seen traveling inside the street. And we went into the official crash test facility here in Switzerland, used dummies, adults, children, and we measured specifically the type of impact that arise when such a device enters into contact with a human. So we looked first at the design of the robot and how the different design will affect differently the type of impact. The design nowadays is quite well made. They really make sure that there is no obtrusive part of the robot, so you don't have things that are edgy. It's usually round and smooth, and it's relatively low weight. The weight is the center of mass is quite low, which reduces the chance for the object to tilt over and then fall onto someone. And this is very good. These are already excellent design requirements. So, knowing this, we looked at here. You have a series of these typical platforms that are already commercial. And we looked at where those platforms would hit this range of pedestrian. And we really wanted to look at a range of pedestrian from small children, 4 or 5 years old, those who may travel in the streets, sometimes alone, to the elderly, and of course, on the range of other pedestrian. Mostly these robots will hit the person at the leg, at the lower leg. But if you look at some of those vehicles, they are still high enough to hit children at part of the body that are fairly sensitive. It's typically the torso, and that's true of young children that are below 1 meter of height. And worse also is that many of those may hit the child at the head or at the neck, which is typical of the most sensitive part of the body. We also looked at women who are pregnant, and we see that there are also good chances to hit just at the region of the belly. So one may want to think about those things in the design. But bearing that in mind, so we went back to the crash facility and designed a crash test in such a way to measure these different region of impact. So we looked at impact on the leg for the adult. What will happen when you hit the adult at the leg? What type of injury can it create? But also what type of secondary injury? Secondary to the shock means when the person falls down and possibly hits his or her head. Then for the children dummy, we looked at the impact on the head as well as the impact on the chest specifically. So we designed the robot in such a way that this will be the only body part that will be impacted. We also tested different speed for the robots to see what was the effect of the current speed limitation that exists worldwide. So first observe that we have a variety of speed limitation depending on the region of the world. And we set to look at one particular velocity, which is about 11 kilometers an hour, so it's 3 meters per second. It's below the speed limitation, but by choosing this one, we take into account that the pedestrian may not be static, maybe running towards you, and then you hit the 6 meters per second. And then we tested a range of velocity between 1 meter per second to 3 meters per second, with the hope that when we really go low at 1 meter per second, we are fully safe, and maybe at 3 meters per second, more danger arise. So we conducted the systematic test that you see here, and we measure the impact force on the body through we have a set of force sensors at different parts of the body, including the head, the neck, and the middle of the body. We also conducted systematic simulation from those systematic tests that we conducted with the children. I don't show all the videos, and the adult dummy. And what we found is that the risk of injury was quite high even when we were at a fairly low speed, even at 1.4 or 2 meter per second for the children. We had a quite a strong proportion of serious injury and skull fracture above 2 meter per second. This is not the case for the humans, although we observed quite a lot of possible injuries when the human falls. And this is an issue only with typically elderly. So elderly have a tendency to fall more easily than other pedestrians, and injuries at the head or elsewhere for elderly is particularly dramatic. So we were a little bit surprised by those data, especially given that those speeds are beyond the speed limits that exist nowadays in the regulation. And so we went one step further and thought, okay, but perhaps this is due to the weight of the mobility device. So we looked at the range of weights of all of those commercial devices that you see here. And again, we observed that we can bring the risk down only if we go at a weight which is significantly lower than what exists nowadays. There would be about 10 kilograms, which is what you find for drones, but it's not what you find for the mobility device around. There are alternatives, of course, to reduce risk, and those are the alternatives on which we work and what we strive to put now forward. This is the alternative, obviously, is to absorb most of the kinetic energy inside the robot. One can do that by increasing the design or changing the design, having bumpers that are very flexible, that can absorb all the shock. And one can also do it by actively absorbing the shock by moving backwards. So, but this is of course areas of research still. They are not available in commercial products, but I would like to take this opportunity to bring awareness that we need this to go forward and to put this into the design and guidelines and immediately to ensure that the deployment of those devices remains safe. Now, there are alternative of things that one could do. We could still limit a little bit the speed, reduce it from the 6 meters per second allowed, now possibly bringing down to 3 meters per second. One could also reduce the weight whenever possible. This is not a bad idea because it will also reduce the energy cost of running those platforms. But of course, most importantly, one wants to avoid collision. And there is a huge amount of work in this. So I'll show some type of work that we've deployed on a robot, but that exists worldwide to avoid collision that are quite successful. But I'll also point out that there are things that robots are still not perfect at, and when they try to avoid collision, they're a little bit sensitive by the type of environment that surrounds them. So this is the robot that you've seen before, and it's mounted with quite many sensors. We've made sure that this robot will have really a full 360 degrees view, and not just planar, but circular. So we've put LiDARs in front, in the back. We've put cameras also in front, in the back. We've put bumpers and sensitive and force torque sensors. So this gives us this full 3D coverage that you also see like that. It allows us to see both pedestrians that are low height, such as children, as well as tall pedestrians. With this, we can run the combination of LiDARs and cameras and be able to perceive the world. I show you this video because I find that it's important for people to see what robots see. Observe that what a robot sees with LiDAR is essentially a set of lines with different colors, and these colors represent the depth of the thing that is moving. From these lines, the robot has to be able to extract patterns. For you as a human, it's pretty straightforward to see that there are humans moving around, but for a computer, it's not that obvious to be able to extract around this set of lines a shape that represents a human. So a lot of work is being done worldwide on this. And usually what happens is one combines this with a detection of people from camera. This is what you see here. You have a camera that is immediately recognizing quite a lot of humans, giving you a little bit of a sense of how far the human is from you. And you can then combine the detection of the LiDAR with the camera, as we see here, to have a prediction of where you humans are. If you pay attention to this video, you'll see that the motion of the human as it's perceived by a robot is not very smooth. The reason it's not smooth is that at the minute, the speed of computation is slow. So basically, the robot sees humans every three frames per second, or sometimes 10 frames per second. So it's a little bit like you walking around and closing your eyes quite frequently for a while and trying to see what surrounds you. So it's still very, very good. It allows us to avoid very rapidly pedestrians in a crowd, in a very dense crowd. And we've done systematic tests in markets in our city and showed that we could avoid almost all the pedestrians because we could run this fast enough. And this has been deployed in different places in the world. But there are things that we've noticed that did not work so well. While the robot could see obstacles very well, one thing that it could not do was to model the obstacles behavior. In a crowd, very dense crowd, especially in marketplace, as where we deploy a robot, behavior of people is a little erratic. You have people stopping to look at things in a stand and then suddenly turning around because they see a friend. You have children who may start running. You have people who stop because they want to check something in their bags. It's extremely difficult to predict. So this we tested even in more difficult condition, like here, when it's a Christmas market at night, because we wanted to see how difficult it was to predict the crowd, and especially when it becomes very dense and when the crowd is behaving in ways even more complex. I can tell you that there, the percentage of collision avoidance performance dropped. It dropped for two reasons. It dropped primarily because the robot had more difficulty perceiving the environment and because it had more difficulty predicting. The most difficult part was the one that you see here. The camera did not work as well, and that we expected this a little bit because at night the density of light reduces, especially when the robot is in a dense crowd. Everything becomes quite dark at the level of the sensor, and so the precision of the detection reduces. Now, there were other things that we missed when we did the test, and these were to recognize other type of object, as you've seen. In fact, in those dense markets, you have all sorts of things. You have bicycles, you have little cars moving around, and we were not prepared to recognize that. We were prepared to recognize essentially pedestrians. So there is a need for improving both the large width of the variety of things that we can detect, as well as improving the capacity of the sensors to work at night. There are other things that we may want to take into account. As I said, we need to model very well the behavior of the type of pedestrians that we are recognizing. A child will act differently than an adult. We may also want to bear in mind that there are parts of the body that are more easily caught, and so when we avoid obstacles, we may want to choose how we avoid the obstacle, on which side we avoid the obstacle. All of those things are still beyond the capability of our robots. So I don't want to give a dark picture. I think we are doing superbly well. We have lots of excellent algorithms to move forward, but we need to be a little careful and perhaps wait before we deploy this platform into very complex environments such as crowd. Because there are also other issues about crowd. A nicely well-behaved crowd, as I've shown before, is fine. There are all the other problems that I've mentioned. You need to see things, you need to see beyond the people, you need to predict a little bit the behavior, but it's fine as it works like this. But what if the crowd becomes a little bit agitated, which is typically the case when the crowd is in a metro station and people are in a hurry to get to the metro? How will the platform react? Do you really want the platform to start reacting like the crowd, to start speeding up with the crowd? But then we have the speed limit, and so it may become quite dangerous if it does so. But if it doesn't speed up with the crowd, the danger is that it will also slow down the crowd or create even more impact. So all of those things need to be discussed, and we need to start developing control systems that are risk aware of these different situations and more cognitive aware of the surrounding. So with this, I'd like to close with a brief overview of what I dream that we will achieve one day, is to make sure that we can have people like this person who stands on this mobility device and has no possibility to control the device outside from just the brain, being completely disabled. So if we could do so, then that means the machine is completely autonomous. So if so, then that means the robot needs to read the user's intention and be able this way to give back all the lost mobility to that person. I think we can go there, and we will eventually go there soon enough. And there will be plenty of benefits for these end users. We just need to make sure that the benefits that we envision for the user do not outweigh the risk to people surrounding the robot. For doing so, as I said before, there are two things that we need absolutely to do. One is to improve the safety of the autonomous control system, and the second is to improve the intelligence of the robot. That means to gain an understanding of the surrounding, of the crowd, of the way that people behave, and to be able to embed this into the robot controller. With this, I thank you for your attention.
Thank you so much, Professor Billard. Can I ask you, we've now looked at robots and devices for outdoor use. What are currently the biggest challenges for constructing robots to be used in a domestic environment, say our home? Are they the same or are they different?
So usually at home, you think of different type of devices. You already have devices that can clean the floor to some extent, vacuum cleaners, and those function fairly well, but they can only really clean the floor, and they have to go around the different furniture, and sometimes you have to help the robot by moving the furniture around. The major challenge is to have robots that can actually pick up the furniture. So at some point I had dreamt of designing a proposal like this with a colleague, to have a robot with two arms that could pick up the chair and then vacuum underneath and then place it back. But that means that the question is, how can you pick up objects, support them, support the weights, because there are a variety of objects. So manipulation in environments such as domestic environment is still a very, very challenging problem. There are wonderful progresses being done. I mean, my lab also work a lot in this area. One can now pick up, to a large extent, a variety of objects. It can be deployed in the industry primarily for picking up boxes coming on conveyor belts as they move, to place them in different environments. That is, to some extent, a technology already. But we see in your own home environment, the challenge is to pick up the object that you have. And each domestic environment is different. The furniture will all vary. Of course, all of us have some sort of typical furnitures. I guess in your country, you all have quite a lot from one brand. I'm not going to name it, but everybody knows what I'm referring to. So that can be useful. One could just take all the product from that brand and assume that they all exist in this environment. But still, that will only make probably, I don't know, 40%, 50% of the furniture. And even if you had those, some are very fragile objects. I'm thinking primarily of glasses, of vase, that are difficult to move around. There are other furnitures that are flexible, such as all the clothes that we wear. They are difficult to pick up because they're slippery, because they are deformable. Those remain challenges both in terms of the prehension and the manipulation, because often our grippers are big. If you look at the hands that robots have, they're twice the size of my hand, but they don't have the strength of my hands. That's a little bit the bizarre thing. And they don't have also all the sensors that we have inside. The tactile sensor, not as good. So this prevents them from being able to manipulate well objects. And then external perception, just being able to see the vision. The problem that I've mentioned about the lack of very accurate vision on robots that move outdoors is even more crucial indoors, because there you need to have very precise eyes, if I may say so, that need to recognize objects.
So another question, a last question. I'm looking for questions from our audience. You here in Stockholm, you can use the QR code. If you're online, you have the question window perhaps to the right side of your screen. Professor Billard, what in your opinion is the role of industrial research and development in terms of robot development? Is the industry addressing the relevant and crucial problems?
So I'll take the first question. So the role of industrial research is fundamental. They are really the link between academic research and the deployment of industrial product and new products. So we do need to have this. It's absolutely fundamental because in academia, we often do not have the time and the infrastructure to look at all the problematic of transforming a very good idea, a very good concept into something that is commercializable. So this is absolutely needed. And it's good that we have this large research center. And they also feed back to the academia by bringing back some key challenges that we may not have seen in advance and that make research go forward.
Are they addressing the relevant problems?
That is more difficult to say because I don't know of all of them, and I think it will. I will remain modest in that respect and assume they do so. But I just want to perhaps take this opportunity to press on people that sometimes cheap is cheap, and I'm surprised by how few sensors are being placed at the minute on autonomous vehicles, because indeed, LiDARs, cameras are deemed to be expensive, and hence we don't put so many of them. But you have to be aware that when you don't put enough of those, then you're creating a lot of black holes. There are regions that the robot cannot see and can't perceive. And this will lead eventually to accidents because pedestrians or people around are not aware of the fact that the visibility of the car is very different. I mean, it sees the world very differently from ours. And once accident arises, as you know, then it fires back, and you may kill a product this way.
Yeah.
So my advice would be to put as many sensors as possible, all the intelligence you can, to start with. And then possibly, if everything goes well...
Professor Billard, we have to stop there. I can see the faces of an appreciative audience here in Kista, and all of our online guests are also thanking you. With that, a warm applause. Thank you so much for joining today.